Okay, so moment distribution is an analysis process that we can use to analyse statically indeterminate structures. So up until now, you've probably focused on statically determinate structures, and with this analysis procedure, we're going to broaden massively the type or the number, if you like, of different structures you're going to be able to analyse. So the process focuses on determining the internal bending moments at joints first. So that's going to be our starting point. As opposed to when we're dealing with statically determinate structures, we go to determine reactions first. Well, this time we're going to determine moments at the joints. So it's a very procedural and intuitive process, and it's an excellent way by hand to check, let's say, for example, computer analysis. So if I was to give you a quick overview of the process, the very first thing we do is we start off, you can imagine in your mind's eye, a structure, a statically indeterminate structure. The details aren't too important here. But the first thing we do is we go around that structure and we fix all the joints. And what that means is we lock them against rotation. So we stop them from rotating. So we essentially create, if you like, that fixed or built-in or cantilever type joint at every one of our joints. So we artificially alter the structure. Then what we do is we determine the bending moments that would develop at those joints in response to the external loading on the structure. Okay. Then we analyse the moments at the joints. And so what we're going to have is at each of these different joints, depending on the loading that's on the adjacent members, you may have a moment imbalance at the joint. Because remember now, you've locked this joint. So the structure on the right will be subject to some loading, and that loading will have no influence on the structure to the left of the joint. So essentially, it's like having isolated structures that are just butted up or pushed up against each other. So at those individual joints, you're going to have moment imbalances. So then for each joint, what we do is we go around the structure and joint by joint, we unlock a joint. We balance the imbalance. So we add a balancing moment to that joint. So whatever the imbalancing moment at the joint is, we go ahead and add the opposite sense of rotation moment of equal magnitude, and we're essentially balancing out that joint. And then we lock the joint. But before we lock the joint, we have to carry over a proportion of the moments that we just applied to the adjacent support, okay, so to the support on the other end of the member. And that's what's called a carryover moment. And that's essentially the process complete for one joint. Then we move on to the next joint in the structure, and we say, right, let's unlock it, we'll balance it, we'll propagate our carryover moments, and we'll lock the joint again. And then we'll go on to the next joint, and so on around the structure we go. So it's an iterative process, which means that we go through all of the joints once, and by virtue of having carried over moments to adjacent joints, we will have imbalanced joints that we just balanced previously. So we're going to have to go through on a second iteration, and we go through around and around on subsequent iterations. And with each iteration, we're more closely approximating the actual bending moment diagram for the structure. Or rather, we're more closely approximating the bending moments at the supports for the particular structure. So what we have is a situation then where we have this very nice procedural process, and it's logical and it's intuitive. And the last thing to say about it, if we're in terms of a summary, is that this whole thing, although it might sound a little bit complicated and a little bit abstract at the minute, we track the whole process with a table. Okay, so we lay it all out in a table, and what can look like very complicated structures, when you put them into the table and you know the steps and you follow the procedure, it all works out relatively easily. So again, I don't know whether that's helped you or hindered you, giving you that kind of a summary. But what I would suggest is, we're going to go through an example now which demonstrates all this. But what I'd have to say to you is, when you get to the end of this lecture and we've gone through this example, you'll understand much more what it was I was talking about at the start. So when we finish the lecture, you should go back and listen to everything I've just said in the overview, because it will make an awful lot more sense after we've been through a worked example. Right, so let's crack on with this worked example. And it's going to be a very basic structure, a very simple structure, but what it does is helps us demonstrate all of the key components of this analysis procedure. So we'll sketch it out. Okay, so this is our structure to start with. Now, straight away, you would look at that and you'd say, right, unless I know this procedure, this moment distribution procedure, or some other procedure for statically indeterminate structures, you couldn't analyze it because there are too many unknown reactions. So it's statically indeterminate, and we can confirm that if we look at the number of reactions. Okay, so the number of reactions is 3 at support A, 3 at support C, and 1 at B. So that's 7. We have 7 reactions. So or minus 3, where 3 is the number of equations of equilibrium that we have at our disposal, is equal to 4. Okay, so it's statically indeterminate to 4 degrees. Okay, so we can't start with determining the reactions because there are too many unknowns, and this is where the moment distribution method steps in. So let's see, let's just throw a title down here. Moment distribution, the actual method itself. So we start off and we initially assume all joints fixed against rotation. Okay, so all joints are going to be fixed against rotation. Again, I'd encourage you to follow along with me and write out your own notes as I'm going. There's definitely some value in this. Right, so if I was to draw the structure again, but I'm fixing all joints, well, I notice that joint A is already fixed, so that's fine. Joint C is already fixed, so what I'm going to be doing is fixing joint B. So this was already fixed. This one was already fixed. Okay, so we've imposed, this is the key bit here, right? We have imposed rotational fixity, okay? Rotational, that's the whole thing here. We're dealing with moments, and so it's rotational fixity we're interested in. So we've imposed rotational fixity at B. Okay, so that's the first thing. So now look at this structure, right? The loading, let's just label it up, A, B, C, D. Right, the loading on AB is now completely isolated from the loading on BC and vice versa. Okay, so what we essentially have is, it's like having two separate beams that are just happen to be sort of slid up and pushed against each other at joint B. So what we have to do now is determine what are called the fixed end moments. The question that we're trying to answer is, what moments for this modified structure, what moments would develop at A, B, and C? And this process is known as determining the fixed end moments. So remember, we've got two separate structures. So we have got something that will look like this. Okay, now, if we think about these as two independent structures, well, we know that a reaction moment would develop on support B like so. This would be a clockwise moment, and an anti-clockwise reaction moment would develop at support A. Similarly, we would have an anti-clockwise on the other side of support B for the right-hand structure, and a clockwise for the right-hand support of the right-hand structure. Now, what we have now is two structures. Individually, these are statically indeterminate. And at this stage, what we're going to do is, and what you'll typically do is, resort to tables of what are called fixed end moments. Okay, and if you're an engineering student for any length of time, you'll be well familiar with these tables, and there will be one provided with this course in any case. But you will pull off from a table for a structure like this with a load P and a span of L, where that would be L over 2 and that would be L over 2. You could identify from a table pretty easily that the moment here would be minus PL over 8. The minus here indicating the anti-clockwise rotation. Similarly, we'd have a plus PL over 8 on the opposite side, where P is the magnitude of the point load and L is the span. And you would pull from the same table the moment for the other side, or the other structure, WL squared over 12 and plus WL squared over 12. Okay, so we can actually put the numbers in here, and we would end up with, this would be, let's call it the fixed end moment for AB is equal to, let me see, that will end up being minus 100 kilonewton meters. And the fixed end moment BA, okay, where the first letter in each case is indicating what side of the structure that we're on. So the fixed end moment BA is obviously going to be plus 100 kilonewton meters. Do the same thing for the far side. We end up with... Excellent. Okay, so we're rapidly advancing through this. So what have we done? We took our structure. Any joint that wasn't already fixed, we fixed it. That identified for us two isolated structures, two isolated substructures. We identified those, or we pulled those two out, and we looked at what reaction moments would develop at the supports in each case. So these are the fixed end moments. So that guy, that guy, that guy, and that guy are the fixed end moments. Great. Okay. So now what we have to do is look at the imbalance. Okay, so there's an obvious imbalance here at joint B. So this is really the heart of the moment distribution method, right? So now what we do is we release joint B and allow it to rotate. Okay, so what have we got? Let's just focus in on joint B for a second and have a think about what's going on. Joint B starts off locked, and then we have a member coming out of either side. Now, the moment on the left-hand side of joint B was this guy. So that was a plus 100, right? So we've got a plus 100 at the joint. The moment on the opposite side, remember this is B, is this guy, which is going to be a minus 208.3. Minus 208.3. I've shown the minus here. That's not necessary if I've also shown the arrow, but just for demonstration, we'll leave it in. Right. Now, if I was to consider what would the bending moment diagram at that joint look like, it would look something like this, right? We would have a moment coming up. That would be for the left-hand side, but then on the right-hand side, we'd have a moment coming up to a higher peak. Now, this is not a valid bending moment diagram. You're not going to see a step in the bending moment diagram like that at a joint here, where only two members are coming in to meet at the joint. So this essentially is our moment imbalance. So that's 208.3, and this value down here is 100. So this is another way of visually identifying, or visually, I guess, displaying the moment imbalance. So that's your moment imbalance. Excellent. So now what we do is, that's the situation we're at now. Then we go ahead and we release. So let's release this joint. Release the joint. Now what do we have? Well, it's gone back to being a roller. Okay. But we have this moment imbalance, which is minus 108.3. 108.3 kilonewton meters. Okay. So our out of balance moment, our out of balance, for future reference, I'm just going to call that OOB. Our out of balance moment is minus 108.3. So if it's not obvious already, I'm assuming clockwise moments are positive and anti-clockwise moments are negative. So that's minus 108.3. And it's going to be important that you get yourself a clear sign convention and stick to it in this method, because signs are going to be very important. Okay, so now what we do is we apply a balancing moment. Okay, so we have our structure again, our roller support. We have our out of balance moment of minus 108.3. And what I do is I come along and say, right, I want to balance that up, because I can't have a moment imbalance at a joint. There must be moment equilibrium at the joint. So I apply a positive 108.3 plus 108.3. And this is a balancing moment. Okay. So now what we have here is the sum of the moments at B is equal to 0. Tick. We're happy with that. We know we must have moment equilibrium at the joint. But now here is the next little nugget, which is key to this method. We have to balance the moment, okay, or rather we have to distribute the moment between the members that meet at the joint in proportion to their stiffnesses. Okay, that is key. I'm gonna write it down, and I would strongly suggest you also write it down. So it's important, right? So what have we got? The balancing moment. The balancing moment is distributed, hence the name, moment distribution method. So it's distributed between the members meeting at the joint. This is it. In proportion to their stiffnesses. Okay, now there is a procedure which we will cover which goes into identifying the stiffnesses of the members meeting at the joint, and it's fairly straightforward. It's nothing to be afraid of. We're going to get there, but to go in and explain that now would kind of kick us off course a little bit. So what I want to do is, for the purposes of just illustrating the whole process, I'm going to say for now, i.e. for just the rest of this one lecture, let's assume member AB is twice as stiff. And what that just means is it's harder to bend. It's twice as hard to bend. Harder to bend, in simple terms, as member BC. Okay, right, what would this mean? So this basically means the balancing moment is divided between AB and BC in a ratio of 2 to 1. Okay, so the balance between AB and BC is a ratio of 2 to 1. Okay, now again, this is just temporary for now for this lecture. In the next lecture, we'll talk about how do I actually determine the stiffnesses. So let's jump back to the example. We had our joint B, and we had the roller. Right, what did we have? Now, the fixed end moments were, let me see if I draw it this way. Fixed end moments were 100 here and minus 208.3 here. So that is a fixed end moment, and that's a fixed end moment. They're the starting point. Then we had our balancing moment of plus 108.3. Now, 2/3 of that go into member AB, which would mean that that is going to be plus 72.2, and that's the balancing moment. And 1/3 of it is going to come into the right-hand member, which is going to be 36.1. Again, it's a plus. Let's draw that on the top. Plus 36.1, and that's a balancing moment, right? So that and that together add up to my 108.3, my plus 108.3. So now what I actually have, if I just sum the moments at the joint, or rather if I sum the moments on each side of the joint, and so joint B is balanced. Okay then, right, now it's almost finished, almost done. The final step is to now propagate through what we call our carryover moments. Okay, so if you've got everything up until now, great. You're 90% of the way through understanding the moment distribution method. To get you the last 10%, let's talk about the what are called carryover moments. Carryover moments. Right. We're going to take a side step from our example for 2 seconds just to talk about what is a carryover moment. Again, start off with a simple structure. Now, if I'm down here at joint B here, right? If I apply a moment M at joint B, I'm going to get some sort of a deflected shape that's going to look like this. Noting here that the moment, or the support at A is a fixed support. And because it's a fixed support, I know that if let's just finish that, tension top, tension bottom. If I apply a moment M at joint B, some of that moment has got to be propagated over to joint A. So there is an effect, there is an influence. This moment of M at joint B has an influence on the support at joint A. And if we were to draw the bending moment diagram, we can see much more clearly what it is. So we've got here, bending moment of M is applied at joint M. And if I was to complete the bending moment diagram for that structure, it would look like so. We would have a moment at the support of M over 2. Okay, it's not a huge amount to this whole carryover moment business. It's pretty straightforward. So if I'm down here at a joint B and I apply some moment to it, if the opposite support is fixed, and in a moment distribution, in most cases it will be fixed, because remember, we're locking all of the joints with some minor exceptions. So if the opposite end is locked, well then if I apply M, I get a carryover of M over 2. So that's one situation. The only other situation is if I'm again a simple structure, but this time I have my roller on the right at B, that's fine. But instead of a fixed support, let's say I have a pin support at the opposite end, at A. Well, if I apply a moment at B again, we have no carryover moment, because we know at this stage, if we've studied bending moment diagrams, we know that there can be no moment developed at a pin support. And so if I have a pin, if I get M applied here, I have no carryover moment. Okay, so no carryover to a pin. Okay, and that's an important one. Okay, so let's just, what were we saying about this guy over here? If we were to just encapsulate what I've shown in this diagram in words, if the opposite end, okay, which in this case was end A, is fixed. So if the opposite end is fixed, we apply a moment at, when we apply a moment at B, when we apply a moment at B, okay, we must carry 50% over to A. Okay, all right, that's it. That's all there is to carryover moments. So let's think about that now in the context of our example. So for our structure, what have we got? Let's just draw out what we had. Right, so we applied on the left-hand side of the support, we applied a clockwise balancing moment of 72.2. Now, the opposite end is a fixed end, all right? So that would mean, so let's just say the opposite end is fixed, so that would mean that we have to apply half of this moment, 72.2, to the far end. So if that was 72.2, well then down here would be 36.1. So that's your carryover moment. Okay, so that is the carryover moment. And then the exact same thing is applied or happens on the other side. We applied a moment of, let me see, 36.1, which would give me a bending moment diagram like this, where that's 36.1, and then half of that is carried over to the fixed end, which is 18.1. And again, that's my carryover moment. So remember, this guy here and this guy here are simply this one and this one, okay, where that was joint B. So that's it. That's all there is to the carryover moments. The last thing we got to do is sum up what are our final support moments. Our fixed end moment we started off with, let me see, that's A. We won't worry about drawing the loads on. We started off with a minus 100 over here. We had a plus 100 here. We had a minus 208 on the far side. Remember, these are fixed end moments that we started with after we locked our joint, and plus 208.3 over here. Then we added our balancing moment to joint B, which brought up, on this side we had a 72.2 added, and on the other side we had a plus 36.1. Then we carried over half of that to here, this fixed support at A, which was 36.1. And again, half of that got carried over here, which is plus 18.1. And the final thing to do is just sum up all of the moments at the joints. And we'd end up with, so we have an anti-clockwise moment at A, which is what we would expect, a clockwise moment at C, which is what we would expect, and the moments at B are balancing each other, which is exactly what we would expect for this structure. So that is all there is to it. Now, what I would say to you is, what I've shown you is the bare bones of the procedure, but essentially that's all. There's not a lot more to it. There are a few kinks and a few sort of exceptions that we have to go through in the following lectures. But what you should do now is go back to the start of this lecture, listen to my summary again, probably watch this lecture at least one more time, just to make sure it's all sinking in and the various different steps are sinking in. But that is more or less all there is to it. What we're going to be doing now is just polishing it up over the following lectures.